Hey, I'm Susanna with Science with Susanna, and today's video is on the integumentary system. So come along, let's get learning. First, why do we even need skin? There are four big reasons. Number one, we need protection. Number two, we need sensation. Number three, we need thermoregulation. And number four, vitamin D production. Protection, let's talk more about that. So, your skin protects you from pathogens, those are disease causers, and abrasions. Always remember, your skin is your first line of defense against getting infection. Whether you're taking beginning anatomy and physiology or you're taking microbiology, remember this theme. Your unbroken skin protects you from disease. Then we'll move on to sensation. Nerve endings in the skin fire signals to the brain, like I've drawn in this picture. So the skin has receptors in it, and they fire electrical signals up what are called sensory neurons to the spinal cord and then the brain, and then you can process your sense of touch. Our skin has receptors that sense touch, of course, light touch, deeper touch, even things like vibration. Also, pressure, light pressure, deep pressure. Heat, we have temperature receptors in our skin, and then extreme inputs are often just perceived as pain. Your skin is important for thermoregulation. Blood vessels that will either dilate, like I've shown in this first picture, or they'll constrict, like right here, in order to release or conserve body heat. And then we have sweat glands, as well as goosebumps. And these can help to either warm us up or cool us off. So I guess I should have said cool us off for sweating, right? And then goosebumps can help to warm us up. Vitamin D production is made from cholesterol only when the skin is exposed to UV light. That vitamin D is required for us to be able to absorb calcium into our small intestine. Your vitamin D is also crucial for many different immune functions, some of which we're really just scratching the surface in order to understand what actually all the many roles are of vitamin D. So you see what happens is when you're exposed to the sun, your skin will make vitamin D for you, and it needs that ultraviolet light in order to pull that off. So now that we've talked about why we need skin, let's look at the three main sections of a typical skin piece. You're going to start with the epidermis. This word, epidermis, is actually translated, epi means upon and dermis means the skin. I've drawn this one in pink. Then the dermis is the second layer. I'm coloring it here in green. Dermis literally means skin. The lowest layer is called the hypodermis, and I'm going to color that one in yellow. You'll also see it in a clinical setting called subcutaneous. So like if you've ever gotten a sub-Q injection, it means that the needle went through the epidermis, through the dermis, and all the way down into the hypodermis. So let's label those: epidermis, dermis, hypodermis. Got that? The epidermis, the top layer, is the most superficial layer of the skin, and it's a tough barrier against pathogens. It's composed mostly of keratinized, keratin is a protein, stratified, that means in many layers, squamous, that means flat cells, and they are considered epithelial of the four different kinds of tissue. So you got that? They are flat cells filled with keratin, which makes it tough, and in many layers. They're also dead, which we'll talk about on future pages too. And these cells are flexible enough to resist, like, when your skin is rubbed on. And we'll talk about desmosomes, or the connections between the cells that help with that, in a coming page. The dermis is the middle layer. It's kind of where all the stuff is happening. So it contains blood vessels, most of your sensory receptors for sense of touch. Your sweat glands start here, your hair follicles, and your oil glands. Now, those things are all in the dermis, but then sometimes, like sweat and oil, the product can go up onto the top of the epidermis. But the structure is doing its work in the dermis. The top of the dermis, the very tippy top, forms our fingerprints. It makes these like wrinkles that are called epidermal ridges, and they form when we are in utero. So even identical twins will have different papillary epidermal ridges. And then the rest of the dermis, so basically most of the dermis, is very tough with the purpose of withstanding tearing. And to help out with that, it's very dense and fibrous. So that means, think when you hear that, think lots and lots of collagen fibers. And they're irregular, like I've drawn in the picture. The collagen fibers are going every which way. And so this all together produces something that is tough and can withstand all kinds of tearing pressures and forces on it, shearing, but it also has room in it for all of these things like the sensory receptors and the sweat glands, the hair follicles, the oil glands. It's a very busy layer. Then the hypodermis is the deepest section, primarily composed of fat or adipose connective tissue. Now we're going to look at the layers of the epidermis. So in this picture at the top, you can see, let's get our bearings. So we have the epidermis is the top, then the dermis, and then the hypodermis. And this page is all about the epidermis. The epidermis is made of keratinized, stratified squamous epithelium. That means that these cells have a lot of a really hard protein in them called keratin. This protein can be cross-linked together with disulfide bonds. The more of these bonds there are, the harder the keratin can be. So you can have a kind of a softer keratin in your skin and a harder keratin in your hair and a super hard keratin in your fingernails. There isn't any blood supply in the top part of the skin. The blood vessels are all in the dermis, and so like glucose and other nutrients have to diffuse upward from the dermis and into the bottom of the epidermis where the live cells are undergoing mitosis. The 5 layers are the stratum corneum, stratum lucidum, stratum granulosum, spinosum, and basal. And the way that we can remember this is a little fun mnemonic called "Come, let's get sunburned." And you can then use those letters to remember the corneum, the lucidum, the granulosum, the spinosum, and the basal. All right, I'm actually going to start at the bottom and move up. The reason I want to do it this way is because this is how the cells are born. They develop in the very bottom. I'm coloring in purple the stratum basal. Now these cells, you'll notice, look practically boxy, and they are undergoing mitosis every single day, making brand new skin cells for you. And then the ones that were just made get popped up a little bit higher, and then up, and then up, and then up, and then up, until we get to the very top of the stratum corneum, and those cells slough off. This process takes 40 to 50 days, depending on, well, I guess it could happen a little faster if you damage the skin, but that's going to be your generic, 40 to 50 days to slough it off. So notice that also within this layer are some melanocytes. These are going to make pigment that's going to protect the cells from damage. There's also Merkel cells there, and these are important in sensory. Okay, so I went ahead and I'm coloring the stratum spinosum, the next layer up, in green. And notice that I've put all these little pink connections between them. Those are called desmosomes. They're a way to connect cells that allows for some flexibility so that we can do this with our skin and not damage it too much. So remember, the stratum basal is making the new cells, they undergo mitosis, and then they get pushed up. And then so each time the stratum basal undergoes mitosis and makes a new layer, the layer it just made gets pushed up. So they go up, 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 like that. And that's this process that you're seeing here. So with the stratum spinosum, these really important desmosomes form between the cells, and also they start to get covered with pigment over their nucleus, so the melanocytes are passing them pigment. Okay, now the next layer up is called the stratum granulosum. I'm just going to color, it's kind of like a light brown. I'm making this, and these cells are really very busy. They are filling with different kinds of oils and keratin. They are becoming keratinized. And so in this process, they're going to start ejecting their nucleus, and they start to lose like their mitochondria and all their organelles. In fact, depending on where you read, you basically start to see that at this point the cells begin to die, and they even can lose their cell membrane. So they're essentially just like covalently bonded keratin, all connected together to make a hard, horny or corny surface on the top of our skin. Okay, now the next layer up is called the stratum lucidum. These cells are now officially dead, and they don't have all the goodies inside of them that make them alive. They're filled with keratin and tend to be a little bit clearer, and that's how it got the name lucidum. But here's the thing, we do not have, like, I don't have stratum lucidum in my arm skin right here. You only have it on like the palms of your hands and your soles and a few other places in your body where the skin is a little bit thicker. But everywhere else, this layer is just not going to be present. Okay, then we have the next layer up, which is called the stratum corneum. That word corneum literally means hard. And these cells are also dead because they died at the level of the granulosum as they move up from there. And they're flat. That's where we get this classic stratified squamous epithelium, is looking at the corneum layers. They're completely keratinized. And if you do like exercises that might cause calluses to form, then the stratum corneum can get even thicker than it is in other places in the body. Okay, now I'm just going to go through this process one more time. So first, the new keratinocytes are formed by the stratum basale by mitosis. And then the next thing that happens is that the keratinocytes are linked together with desmosomes so that they are held together in sheets, basically. I had a coworker tell me that this helps her understand what happens when you get burnt and you kind of can peel the skin off, almost like layer by layer. It's those desmosomes were linked, and then it gets peeled off, and the cells hold together. Then the next layer up is when the keratinocytes are filled with keratin, they lose their nucleus, they die off. And then after that, they provide a protective barrier for you for about 40 to 50 days, after which they are sloughed off, and you're always making new ones. This page right here is a good example of thick skin. And I just want to do a little shout out to Brian Bitch, who I have never met, but I appreciate the work that he did on these labeling these slides, and I think he might have even prepared some of these samples. So when you look at this, you can see that this thick skin, thick skin is only going to be found in certain areas such as the palms and the soles of the feet. And in both pictures here, you can see the stratum corneum is going to be on top. And then the stratum lucidum, see how it looks a little bit clearer? So it's got called lucidum because it looks clearer. And then that very busy stratum granulosum layer that is visibly dark because of the way that the proteins are being produced in it. It will stain a little bit darker when it's prepared as a tissue sample. Then we have the spiky stratum spinosum. And then last but not least, what Brian in this picture is calling the stratum germinativum is what I call the stratum basale, and that is the layer undergoing mitosis to make you new skin cells all the time. Now the dermal papillae, this is where I told you, remember the very top of the dermis has kind of wrinkles to it, and that's where we get our fingerprints from. The thick skin has stratum lucidum, thin skin does not. Thick skin lacks hair follicles, oil glands, erector pili muscles. See right here, you don't make oil right here, and you don't have hair right here, do you? You also can't get a goosebump right here, so you don't have an erector pili muscle on those particular parts of the skin. But thick skin will have eccrine sweat glands, so you can sweat here. And eccrine makes a watery sweat that helps to cool you off. And I love it in this slide right here. You can actually see a twisty eccrine sweat gland. And it makes the sweat, and then it uses exocytosis to send out packets of sweat. Now on this page, we'll move to the next layer, the dermis. The papillary region of the dermis forms the epidermal ridges that we call fingerprints. These are unique fingerprints. The reticular region primarily contains dense, fibrous, irregular connective tissue. Then you come to the dermal blood vessels. So I'm coloring here a red and a blue blood vessel. Red generally indicates arteries, blue indicates veins. Now we'll draw in blue a sweat gland. And I'm going to show you two kinds of sweat glands in this slide. Okay, so you've got hair follicles, and the hair follicles always have an oil gland attached to them. It's called a sebaceous gland. And they also will often have a smooth muscle called erector pili muscle attached, and that can cause a goosebump when it contracts. And then the dermis also contains nervous supply. The dermal blood vessels are going to provide the nutrients. They have to diffuse upward to the stratum basale of the epidermis. And they can vasodilate. So here I'm drawing one that's kind of getting bigger, and it's able to then release heat in the skin so that we can cool off. Or they'll vasoconstrict. They'll constrict and get tighter, and that's how we can keep warmer, by keeping more of the blood in our core instead of out to our skin. The sweat glands can either the eccrine sweat glands that are watery, and they're meant for evaporative cooling, or apocrine sweat glands, which become active at puberty, and they're the ones that are associated with causing body odor because some of the ingredients are really good at growing bacteria. Then we have the hair follicles. They're moisturized by sebaceous or oil glands, and those erector pili muscles can cause goosebumps. The nervous supply is going to have motor or efferent control that is going to do things like regulate sweat gland activity, and also able to contract the erector pili muscles. Then we also have sensory information known as afferent. This is going to be signals that provide sense of touch, pressure, vibration, temperature, pain. They take that information to your brain so that you can process your sense of touch. Now I'm going to look more closely at sensation and how these skin receptors work. So first off, sensation. I'm going to draw the layer of the skin here, so you might be used to seeing this by now. This top part is the epidermis, and then the middle layer is called the dermis, and the dermis has most of the sensory receptors. They have cells called Merkel cells. Some books will call them Merkel discs, and these help you sense touch and texture. They're very slow to adapt, and what I mean by that, and I put slow to ignore, it means that if you're typing, like, you don't really forget what something feels like, and so you don't start ignoring it. Whereas there are other kinds of sensory receptors that are fast to adapt. So like if you keep touching something, it's almost like you're not even aware of it anymore. And I think it's just a way for our brain to decide what's important to pay attention to and what do we need to ignore so that we can go about the business of life. Now, a nerve is when you have many neuron axons that are bound together like a thick wire, and they're going to take information either to or from your brain. And so the reason I'm mentioning that definition here is because in the skin, you're going to have a variety of nerve endings, right? And they could potentially all leave along the same nerve pathway. Now, there are lots of free nerve endings that are coming from the epidermis, and these are going to involve things like your nociceptors, those pain receptors, and also thermoreceptors that help you to sense temperature changes. Then there are the Meissner corpuscles. These, like the Merkel cells, notice they both start with an M too, are also important for touch and movement. The biggest difference that I found is that the Meissner corpuscles are fast to adapt and ignore. So they're going to stop telling your brain to worry about whatever is touching them. So again, you have some that never stop telling your brain what's touching the skin, and then the Meissner will be like, yeah, that's been sitting on the skin for a while, I'm not going to worry about it. So we have two different approaches to how these receptors fire and send their information. Okay, then we have the lamellated or Pacinian corpuscles. These are going to fire their action potentials when there is deep pressure or vibration. And I think about this as like even if you were deaf and you can feel the beat, the vibration of loud music in a room. And I had a coworker that told me that she thought of like, when your cell phone vibrates in your pocket, that is going to trigger these lamellated or Pacinian corpuscles to fire information to the brain. Then there's something called a Ruffini corpuscle, and this is going to help fire action potentials when your skin is stretched, maybe a little too much. You might start to feel some pain from that, and then also deep pressure. So look at all these ways that we have of receiving sensation because we have skin. The next thing we'll talk about is thermoregulation. So I'm going to draw a little character here and use this character to show you how we can use our skin for thermoregulation. So when body temperature rises, a few things are going to happen. Okay, thing number one, free nerve endings in the skin will sense temperature changes. They're going to fire electrical signals up to the hypothalamus, that's in your brain, and your hypothalamus will respond with sympathetic signals back to stimulate your sweat glands. So it's some motor output to make you sweat. So I'm going to show you a few examples so you could sweat through various parts of your body. In your skin, you have these eccrine sweat receptors that make this watery sweat. So sweating allows for evaporative heat loss from your body. As the water evaporates off your skin, it cools you off. It takes a little bit of heat with it. Okay, then you're also going to be able to cool off if you're too hot by dilating the dermal blood vessels that are in your skin. And this is classic, right? We all know you're working out or you're hot and your face will get flushed. So just like I'm drawing on this girl, this flushing that is going to help her to dissipate heat from her body. So increased dermal blood flow allows radiation heat loss. So if you ever put your hand right here when your skin is really hot and you can almost feel the heat waves coming off of your skin. Then another interesting adaptation we have when we get too hot is your hypothalamus can actually decrease your metabolic rate, because if you're not making as much ATP, you're not going through as much fuel and you won't be making as much heat. Okay, now I'm going to draw this girl again, but this time we're going to think about what are some things that will happen to her if she's too cold. So now her body temperature is not high enough. Free nerve endings in the skin will sense temperature, just like before, but this time, when they send their sensory electrical signals up to the hypothalamus will respond by sending back signals to stimulate the erector pili muscles. The erector pili muscles will cause what you know as goosebumps. And these, not only do they have a little muscle movement, which in and of itself can generate a teeny bit of heat, but the hair that stands up on your arms can actually help to trap heat close to your body. And this works better if it's like a cat or a bird or something, right? And it can really trap a lot of heat, like with downy feathers, for example. But it does do a little something for us too. Now, the next thing is that we'll have a constriction of dermal blood vessels. So see how I'm drawing on her, like her lips turned blue and her fingers turned blue? Decreased dermal blood flow will help to conserve body heat. And then to talk about the hypothalamus and our metabolism again, the hypothalamus will actually increase your metabolic rate if you're cold a lot in a way to hopefully generate more heat, and you'll have a faster metabolism that is generating more heat. That's what I meant to say. And then one other thing is that you'll have motor output that causes involuntary muscle contraction. You'll be shivering, which generates heat. Have you ever been so cold that you are just shaking and you don't want to, but your body's doing it involuntarily? That's what's going on here. So of course, shivering. So I'm trying to show you she's shivering with a little bit of these purple lines. Shivering contracts skeletal muscles to generate heat. And I'm bringing this one up even though this isn't technically part of the dermis, but these the sensory information is in the skin. that lets your body know how cold you are. And then the shivering can be actually skeletal muscles that start to respond in this case. So it's a little bit more complex, but still applies. On this slide, I get to talk about one of my favorite jobs of the skin, and that is making vitamin D. Vitamin D production requires the sun, and as you can see, what's going to happen is that UV lights from the sun will hit our skin, and when they hit the living keratinocytes in the stratum basal and the stratum spinosum, it will cause the cholesterol inside of those cells to be converted to vitamin D3. And then that vitamin D3 can travel in the blood to the liver for modification and then to the kidney for its maximum activation and all of the important jobs that it has in our body. A few of the key functions of vitamin D, just to keep it simple. Number one, it makes it easier for us to absorb calcium from the foods that we eat into our bloodstream. So they're broken down in the small intestine, the calcium's there, but without vitamin D, not enough of it will be absorbed into the bloodstream in order to be put into the hydroxyapatite crystals in our bone or the calcium that we need to have in our bloodstream and around our cells for muscle contraction and nervous signaling. It also has numerous roles in healthy immune response. So for example, having healthy vitamin D levels is very predictive of how someone might do if they suffer from a respiratory infection or whether they even get sick. But if they do get sick, how long they might be sick. So vitamin D levels are really important during those winter months. And then the vitamin D seems to have some complex roles in maintaining cardiovascular health, probably for a variety of reasons that I won't go into now, although I do have some thoughts on it, of course, right? Next up, we'll talk about UV light in your skin continued, and specifically with melanin, or the pigments in our body. So what I've done here is I've drawn some layers of the skin. So that big yellow thing on the bottom is a melanocyte. And then I'm putting blue nuclei into all of these cells of the purple stratum basal and then the green stratum spinosum. So we've got stratum basal on the bottom, and then I have a few layers of the stratum spinosum cells. And these purple ones in the basal, call these the stem cells because they're going to be making more and more new keratinocytes. So it's that bottom layer undergoing mitosis every day. And then here's one example of a melanocyte, and you have these multiples of these throughout the stratum basal. So the melanocytes are going to make the melanin that you know in your body gives you your skin color, your hair color, your eye color, and you even make a form of pigment in your brain, which has different roles, but it's important there. So the melanocytes in the stratum basal produce melanin, and I'm drawing these little dark spots to represent the melanin. And then the melanin can come in forms of blacks, browns, and reds, so that's why we can have all different kinds of skin color, hair color, and eye color. Each melanocyte can deliver melanin to many keratinocytes. I think I read like maybe each melanocyte can be hooked up to about 40 keratinocytes. And it's going to mostly connect up, as you can see in my drawing, to those keratinocytes in the stratum spinosum. Then the keratinocytes phagocytose the melanin and position it over the nucleus. So what I've drawn here is what happens is the keratinocytes can phagocytose these little packets of melanin that are it's actually an organelle called a melanosome. And then they can use their cytoskeletal elements to position it over their nucleus. The melanin protects the DNA of keratinocytes from mutation by UV radiation. That very ultraviolet light that needs protection, our DNA needs protection from, is what stimulates the melanocytes to produce extra melanin, resulting in a tan. So you're going to have a genetic baseline of how much melanin you normally have, and then you have an ability to produce extra melanin when you're exposed to UV light. The desmosomes are going to connect all the cells within the epidermal layer. So I draw these with red lines. And remember, these are cellular connections that help hold the cells together. Only the stratum basal and the stratum spinosum are shown in my little drawing here. So melanin can actually break down as it rises to the surface in the stratum corneum. And it tends to break down in fairer skinned people more quickly than it would in darker skinned people. So you're going to have less melanin in that stratum corneum compared to what you had in the stratum spinosum, for example. Skin color is also influenced by your diet. So, certain fruits and vegetables have orangey colored carotenoids, and those can cause a pigment in your skin, more of an orangey color. And then also the amount of hemoglobin or red pigment in your blood cells, that can have an impact on your skin color, especially again if you tend to be more fair skinned. It's going to give kind of a pink, maybe, or a rosy color. And I also wanted to say that they've done these studies now, and they'll take a bunch of people, show you a picture of them, and then they'll use like Photoshop to change the amount of orangey pigment in the skin from the carotenoids. And they find that consistently people think that the people with more carotenoids in their skin are more attractive, and they think it is an indicator of like a healthy glow, right? That you're eating more nutritious foods, and then that orange will, it's very subtle maybe, but could still show up in your skin color. Now, because I think it's interesting and you might think of pigments, neuromelanin is a dark pigment that's produced in the substantia nigra in the dopaminergic neurons in your brain. Sorry, I have a little typo there. So just say substantia nigra, not substantial nigra. And that is in your midbrain. So it's inside of your brain where we have some control over our fine motor movements. And that pigment there is essential for the function of those neurons. And without it, then people start to develop the symptoms of Parkinson's disease. So pigments in our body are much more than just how we look. There are important physiological components to what they do. All right, so let's talk a little bit about some abnormal skin colors. First, jaundice. And jaundice is going to be an abnormal yellowing of the cornea or of the skin. It generally indicates liver dysfunction. Cyanosis is a bluish color in the fingers and maybe the lips. And it usually indicates oxygen debt, which I don't know if I forgot to put that on here, but maybe it will come up later. And then there's erythema, and that is an abnormal reddening due to vasodilation. It usually indicates some kind of inflammation, like with lupus, or infection with certain, like scarlet fever, let's say. Oh yeah, so the cyanosis, back to this other part in blue, indicates low oxygen in the blood. I just had it show up at the wrong time. And then pallor, that just means that you're pale, abnormally pale skin and mucous membranes, and it can indicate anemia or maybe a poor blood supply to that particular area. On to nail structure. So I have a little cartoon nail for you and then a picture of an actual nail, and I'll try to show you the basic structures here. So we'll start with the nail plate. That's probably the easiest. When you think of your fingernail, you're thinking of the nail plate. It's the hard part on top. So I'm labeling this on these 4 different images that we have here. This is the nail plate, right? It's the actual rows of dead, highly keratinized stratum corneum cells. It's essentially pure keratin protein because by this point, even the cell membranes are gone from these cells, and you just have keratin that's like cross-linked with disulfide bonds to make it really, really hard and strong. Now, underneath the nail plate is the nail bed. These are living keratinocytes that are underneath the nail plate. They don't produce them, but they are supporting them underneath. They don't make very much keratin like normal cells of what we would call the skin, right? And they never slough off because they are covered with the nail plate. So they have a very different life cycle than what we learned about in the regular skin. Then the free edge is what we call the part of your nail that you can clip. It grows past the end of the nail bed, and because of that, then you need to have a way to seal, right? Where does the nail bed end? Because that's got a lot of nerve endings in it. So what you have is something called the hyponychium, and that literally, hypo means under in Greek, and nychium is the claw. And so hyponychium means under the claw. And it's skin that seals under the fingertip up to the nail plate to protect the nail bed. And this seal is lost when the nail gets too shorn or is cut to the quick. I think I meant to put too short, but anyway, you maybe heard that phrase, oh, it cuts to the quick. And that's when the nail, maybe you ripped it and now the nail bed, it's so delicate, is revealed. When you clean under your fingernails, you only clean up to the hyponychium. You don't want to puncture that or go through because, again, then you're into the delicate nail bed. If people bite their nails, then they can damage their hyponychium. Okay, now the nail matrix, this is where the actual nail plate is produced from. So these are very similar to epidermal stratum basal cells that are undergoing mitosis, and they are getting moved forward on the nail. So instead of up like they are on the skin, they're getting pushed forward, and they are being filled with keratin to the point that the cells end up dying. So they are alive when they're being produced because mitosis requires living cells, and then as they get keratinized, they die off. Now notice that you can see part of the nail matrix, but part of it is actually underneath that top layer of your skin. And the part that is visible is what you call the lunula. Lunula means moon, and you can see that half moon generally on your thumbs. Some of you might be able to see it on all your other fingers too. And it is clear looking, or even white, because it has so many of these stratum basal mitotic cells that there's like many thick layers of them that it obscures the underlying blood vessels and looks really pale to the eye. Then there's the eponychium. So notice that you have an eponychium, and a hyponychium. Epo or epi means upon, nychium means the claw, so it's upon the claw. This is the delicate thin skin that produces the cuticle, and it helps seal the space between the nail matrix and the nail plate. So again, it's like this little protection, like a little barrier. Now, when you go to get your nails done, and they'll clip at that sometimes, at least when I've gone, that's what I've noticed they do, and I don't really like it. And as I've been reading more about the nails, you really shouldn't mess with that too much. You could push it back a little bit if you want, but you want to leave that eponychium alone. It's meant to protect you from getting infections, and certainly we know that it hurts. The thing is, a lot of people think that that is their cuticle. It's actually not your cuticle. Technically, the cuticle is produced by the eponychium, but it is completely dead cells, the stratum corneum cells that seal the nail matrix, and it can accumulate on the nail plate. So if you look on a nail, you might see little bits of dead cells that you can completely scrape away. That is your cuticle. Now, the truth is that you're probably going to hear people that do nails call the eponychium your cuticle, whatever, but technically they're not the same thing. So here's a summary. I just have this picture here. You've got the nail plate, the lunula, the eponychium. Notice in this picture they didn't even try to put the cuticle, but it would be like just little bits of dead cells that you might see on the nail plate itself that you can scrape away. Then here you've got the nail matrix that produces the nail plate. The nail bed is underneath the nail plate. The hyponychium is the skin that seals where the nail bed ends so that you don't cut to the quick right there. And the eponychium seals where the nail plate ends right here and where the rest of your regular skin is. Hair structure and types. So first let's start with the hair shaft. So the hair is going to come out of the dermis. It's going to go through the epidermis and onto the top of your skin. The hair shaft will have a middle part called the medulla. I'm going to color this kind of a mustardy yellow. The medulla has soft keratinized cells, and baby soft hair, it's going to almost always just be this soft keratin. But most of your hairs on your head and other parts of your body have also what's called a cortex. This is really where all the action is. These cells have a ton of keratin in them, so of course they're very dead once they become this keratinized. And this is where you're going to have your pigment. So whatever color your hair is, the cortex of each of your hair shafts is where that pigment is. Then you do have a cuticle that is around the outside of the hair shaft, and that is like dead cells that are overlapping, like shingles on a roof. And so if that gets disturbed by like coloring your hair or maybe brushing it too hard, then you can get what we would call a split end or frayed if the cuticle starts to come apart. Interestingly, the cuticle doesn't have any pigment in it. Isn't that interesting? So when you see the pigment, you're actually seeing the pigment that's in the cortex of your hair shaft. Now, where does the hair shaft come from? It comes from these cells right here, this matrix. It's kind of like equivalent to the stratum basal of the epidermis, but these cells are the mitotic ones, so that's important. They're going to produce the keratinocytes of the hair shaft, the medulla, the cortex, and the cuticle. And so different cells in the matrix are responsible for either making the medullary cells, the cortex cells, or the cuticle cells. And within that matrix are the melanocytes that are going to make the pigment for your hair. This hair shaft cortex keratinocytes can have blacks, browns, reds, like these variety of different pigments. Both the color itself can be different and the amount that you have. Then all of these mitotic cells in the matrix need a whole lot of nourishment, right? So the papilla is part of the dermis that is actually feeding and nourishing the matrix to keep it alive. Outside of the hair shaft is the hair follicle. I typically think of it as kind of anchoring the whole hair into the skin in the dermis. But it turns out there are regulatory cells there too that do influence the making of new parts of the hair shaft. The outside of it is epithelial cell in origin, and it's what we call the epithelial root sheath. And then the inner part is called the dermal root sheath. And both of these parts are just kind of supportive around the hair shaft itself. Now, the hair shaft is going to keep going up and out of the body, but the hair follicle is going to stay down in the skin. Now, I'm going to talk about 3 kinds of hair types. The first is lanugo. This is what your unborn body had. It's soft, it's unpigmented, and so it's not going to have very much keratin in it because to make it so soft. It's going to cover that whole baby's body when the baby is in the uterus and constantly exposed to the water of the amniotic fluid. That, as you know, you could get all wrinkly from being soaked in water, right? So this lanugo helps to protect the baby, and also the lanugo anchors that waxy vernix caseosa, and that keeps the baby from getting all wrinkly from the amniotic fluid too. And then the lanugo kind of traps that wax onto the top of the baby's skin. Most of that lanugo will fall out before the baby is born. Then vellus is what we call peach fuzz. So this is also going to be a really soft hair that you're going to see. You mostly hear peach fuzz when they talk about boys, right, that haven't got their beard yet. But all of us have peach fuzz. So like the hair on my arms is mostly peach fuzz, and you have it on your face if you see certain light and angles. So we do have this on a lot of our body. It just doesn't have very much keratin in it, and relatively speaking, and it can't get very long. So peach fuzz is always going to be short hair. It's soft, it's lightly pigmented, it's short, and it doesn't have any oil glands in it. It will cover most of your body. Remember we talked about the thick skin though? It's not going to be on places like that. Then there's the terminal hairs. These are like the hairs on your head, your eyebrows, your eyelashes. If you're a man, it's going to be your beard hairs. It's going to be pubic hairs, and some of like your arm hairs and leg hairs will turn into terminal hairs too. So it's thicker, it's coarser, it can be heavily pigmented, it can be long. And during puberty, many of your vellus hairs will transition to terminal hairs, both on your arms as well as the development of pubic hair. And then for men, they're going to get their beard hair is vellus hair that transitioned to terminal hair during adolescence. Testosterone is the hormone that causes the hair to change from vellus to terminal. And the very testosterone that causes us to get more terminal hairs can actually destroy and kill the cells of the hair follicle, leading to what we call male pattern baldness. It particularly happens, on the crown of a man's head as he gets older in some men. All right, we're kind of nearing the end of the integumentary system. We need to talk about burns. Burns can be classified as first-degree burns, in which case only the epidermis is affected. You've all had one of these kind of burns. It's mildly painful. You might run it under cold water. It might turn red. Then there are second-degree burns, and these ones are going to affect not only the epidermis, but part of the dermis. So sometimes they're called partial thickness burns. And you'll have blisters that form here because the epidermis will actually separate away from the underlying dermis because they're different kinds of tissue, right? One is more connective tissue and one is an epithelial tissue. So they separate, and then inflammation causes, or should I say allows, fluid to seep into that space and form what you know as a blister. Then there are third-degree burns. Third-degree burns are also called full-thickness burns, and it's going to penetrate all the way through the epidermis, the dermis, and the hypodermis in at least one spot. The nerve endings, like the Merkel cells, the Meissner corpuscles, the free nerve endings, even the lamellated or Pacinian corpuscles, all of these could be destroyed in the burning through of the dermis, and so you won't have immediate pain. However, over time, as the burn heals, those nerve endings can regenerate as long as the cell body is safely near the spinal cord. And if they regenerate, and as they regenerate, it can cause a lot of discomfort. Hypovolemic shock is the most acute danger because when you lose your skin, you are going to have a lot more evaporative water loss. And so the body is going to become dehydrated, and it can become so dehydrated that blood pressure can no longer be maintained, and the patient actually is most acutely likely to die of hypovolemic shock. Now, if they survive that, then in the coming days and weeks, infection is the ongoing concern. Because remember, as I've said to you, your unbroken skin is your very best defense against infection. In third-degree burns, because the entirety of the skin has been burned through in that spot, then as it heals, it's going to heal as scar tissue, and it might be necessary to do a skin graft from somewhere else on the body because the scar tissue can't stretch like your skin can. Remember those desmosomes? Now, burns are measured or quickly estimated with the rule of nines. So if a patient comes into the emergency room, they're able to quickly estimate how severe the burns are, and that will help them to estimate how many IV bags and fluid replacement is going to be needed to help that patient. So you can see that the head and the neck are classified as 9%, and then each arm is 9%. But remember that the front of the arm would then be 4.5%, and the back would be 4.5%. And then you have with the legs, the front of each leg is 9%, and the back of each leg is 9%. So altogether, a leg is 18%. So just keep that in mind. I've noticed that in introductory anatomy and physiology exams, there is oftentimes a question where you're asked what percentage of a person's body is burnt, and they'll give you a picture like this. So just make sure that when you're answering that question, you're paying attention. Is it just the front of the leg, or do they say it's the front and the back of the leg? Pay attention to those kind of things, and I think you'll do fine on that. Skin cancer is classified according to where it originates in the skin. Like all cancers, it's an abnormal growth of cells, might result in a tumor. In this case, the tumor might look like an overgrown mole, and you're going to be having abnormal mitosis, too much of the mitosis. And it's going to involve mutations in the DNA that cause those cells to have different traits than normal healthy cells. Skin cancer is actually the most common type of cancer in the US, but the good news is it's very rarely deadly. Melanoma, as I'll show you in a second, is the kind that is the most dangerous. The most common kind, 80% of all skin cancers, are basal cell carcinomas. This is where the cancer originates, unsurprisingly, in the layer of the epidermis that is producing new keratinocytes. So it's called basal cell carcinoma because it's the stratum basal cells. The good news about this is it's extremely unlikely to metastasize, far less than 1% chance that it's going to try and move anywhere else in your body. And that's when cancers can lead to death, is when they start moving to other places in the body and taking up residence there. The second most common kind of skin cancer is squamous cell carcinoma. Now, this is primarily going to be associated with mitosis that it's occurring in the stratum spinosum. Now, remember, that should not ordinarily be happening, right? The stratum basal is where the cells are coming from. But in the stratum spinosum, those cells still have their nucleus and their DNA, and so they can abnormally divide, even though in a healthy situation they would not be doing that. About 19% of skin cancers are in these keratinocytes that are other than the stratum basal. But note that keratinocytes in the stratum lucidum and corneum are dead, and therefore they are never going to be cancerous. The stratum granulosum could rarely be involved. These cells are in the process of dying, so they're very unlikely to start going through mitosis, but it's not impossible. In that case, a doctor would probably tell the patient that they have squamous cell carcinoma. Then we come to melanoma, which is a scary kind of cancer. It's the least common kind of skin cancer by far, but it's the most common kind of skin cancer that could kill people. Only probably less than 1% of skin cancers are melanoma, and that's when the melanocytes start to divide inappropriately. And melanocytes, you might recall, they have these processes. They're actually called dendritic processes that go out and reach in toward the stratum spinosum, and then they send out their melanosomes that have the melanin in them so that they can go into the keratinocytes to protect them, right? But because the melanocytes have that kind of creepy crawly ability, they're able to creepy crawl right into your bloodstream and then move to another part of the body. And that's why they are more likely to be metastatic. Now we have something called the A, B, C, D, E characteristics of melanoma. These include things like asymmetry of the mole, the borders of the mole are irregular, the color changes in different parts of the mole, the diameter is greater than 6 millimeters, and it's changing over time. The colors are changing, the size is changing, the borders are changing, etc. These are all going to be red flags, and the more of these red flags that are occurring in a mole, then the more concerning it is that the patient could have melanoma. So we did it. We got entirely through the integumentary system, and I feel like I covered everything that you would typically be asked about on an introductory anatomy and physiology exam. So go get them. I hope you do well on your upcoming exams, or if you're just here for fun, I hope the rest of your day goes great.